Hi everyone, this is Aravind Gopal Malapareddy. I'm from Juspay. I work as a software developer in Juspay from the last 3.5 years. Just a moment, let me present the screen. So today I'm going to be talking about more like in giving an introduction to functional programming. So functional programming might be few people have already heard it and few people might be hearing for the first time. So simple in simple terms, functional programming is nothing but applying functions to an arguments and composing those functions. So in functional programming, functions are the first class citizens. It means you can pass functions as an arguments to another function and can be written as an output from another function, right? See, might be few people might be already wondering why there is another language like at another languages, right? I'll gonna be talking some of the basic basic things that says why Haskell is something we choose and many people were choosing across the world, and it seems like something can be useful to solve bigger problems and bigger challenges that's gonna come in way, right? So the very first thing is it's actually based on lambda calculus. So that means it's actually backed by mathematics. So in a way, how do we see it is, so when I say I'm writing Haskell program, or when I say I'm writing a functional programming language based program, right? All I'm saying is you can consider it as I'm writing a proof for a problem. I'm writing a proof that this is my solution. If I can prove it, that means the solution might work in 90% of the cases, unless you have some logical bugs. So I'm not talking in terms of logical bugs, but at least at the 90% of bugs because of the types or because of null pointer exceptions or any of these terms, right, wouldn't be there in functional programming languages because it is a proof, right? So let's consider that I have a Pythagorean theorem, right? So it's not like, okay, if I go to Mars or some other place, that Pythagorean theorem doesn't work, right? Because it have a solid proof. And at the same time, you have some other kind of theorem where the proof was kind of depends on the environment. So when it changes, the output changes. So you can see the program in the same way, right? So when it works in your laptop and it doesn't work in some other people's laptop, it's because your code was not proven across. It's proven for a specific value. Even the test cases can be seen it in the same way, right? So other than just being backed by mathematics, so it is a pure, so there is this concept of purity in functional programming languages. So what do you mean by purity? See, a function is called pure function if it returns the same output for a given input how many times, like no matter how many times you have called it. So you consider a function called add, right? Which would take two integers and return back an integer to you. So you call add with values 1 and 2, right? Irrespective of times, irrespective of how many times you have called add 1, 2, it's always going to return you 3, right? See, these functions are called pure functions. Okay. See, laziness is to be honest, is a bigger concept, but you can interpret it in a simple way, right? Unless you ask for the value won't be computed. So let's go back to the previous example, right? I said add is a function that's going to take two integers and return back an integer. Um, See, unless you are using that value, add won't actually compute it. It will just remember how to compute it, right? That's called laziness. It might be look a little bit awkward in the first place because you don't see it usually in any other languages, because our mental model was more like this, right? Whenever I call add, it should return me back a value, right? We don't have this concept that it's going to return you back return you back how to compute rather than computing 5, right? So that's called laziness. I'm going to skip modularity for a moment. Let's go to immutability. See, immutability is nothing but you have a variable and you can't change it, right? So you define, let's say variable a is 5, then you can't change that variable a to 6 or something. So it's simple, right? Side effect separation. See, it's interlinked with purity. So what do we mean by side effects is, I guess everyone understand what is a pure function, right? A function that takes the same input and returns back the output irrespective of how many times you have called, right? But let's say the add function that we talked about before, right, is happening somewhere in the outside of my system. So let's say it's an API call. I'm doing an API call with 1 and 2, right? And the add function is actually happening on the server and it returns me back the value. Is there guarantee that every time I get a 3? To be honest, no, right? Because what if internet went down, or what if the server was taking more time and the timeout happened and the connection was reset, or I gave a wrong URL. Let's say I just gave a wrong URL, or I just gave wrong data in terms of the structure of the data rather than the values, right? It won't give me back the same output every time I call with the same input, right? See, anything can happen because it's not under my control, it's outside of my system. So you can see these functions as side effects, right? So there is this clean difference in functional programming, what are pure functions versus what are impure functions, right? We call them side effects because they can affect something else. So a simple example could be, let's say I'm reading a file, right? I said read file abc.txt. In the same code, in the same set of statements, after 10 lines, I again said read file abc.txt. Is there any guarantee that I would get the same output from the file as I read before? Actually, no, right? Why? Because after I read, I am doing 10 more statements, and meanwhile, someone can update that file, right? So when I read for the next time, even though I'm giving the same input, right, the file name as an input to read file function, I won't get the same output. Why? Because someone else has changed it. So not being under my control of everything can be considered as side effects, right, which can be affected by someone else, right? So there is this clean separation between pure functions and side effects or impure functions, and hence Haskell is one of the see, when I say Haskell, I meant all the functional programming languages in a way, but since I'm using Haskell as my base, so I use Haskell repeatedly. So so Haskell is a language where identifying bugs is more easier, because so let's say you wrote a code and there is a bug, right? And you found that this bug is happening in random times, right? Then you are pretty sure that this is not happening in purity. Why? Right? Because why? Purity will always give you back the same output for the same input, irrespective of the world is breaking, right? But if you talk about side effect functions, you give the same input, you can't expect the same output every time. So I intuitively know that what are all the functions to look at rather than looking at a huge code base, right? Let's say 40% purity and 60% impurity. I'll go look at only the 60% impurity guys and make sure there is nothing else breaking over there, right? Cool. So the next thing is higher order functions. As I already mentioned, functional programming is nothing but playing with functions. So higher order function is nothing but you can pass function as an input to another function, and also return function as an output from another function, right? So I actually skipped one concept called modularity. See, many people might think, even if I'm writing in some other language, I can still write a modular code, right? See, what is modularity in a simple terms people will say is, Right? Okay, I have a big problem. I'm going to break it into chunks and I'll write 10 functions rather than one function. See, definitely that can be considered as a modularity, but there is this mental model, right? Like you explicitly thinking that you wanted to write a modular code. But that's not the case in functional programming language, right? See, the by default, the base, the crust that was created for you by the functional programming languages is by default modular. Why? Because again I fall back to the statement of what is functional programming, right? See, functional programming is nothing but applying functions and composing functions. See, it's always about composing functions. So by default it's giving you that impression that you can compose any kind of function. See, that's the reason why like by default you would tend it towards writing a modular code rather than one big chunk of code, right? See, all these things will help you when you're writing code also at a higher scale rather than as a single person. If you're writing as a 10% team or 20% team, or as it grows 100 people team or 200 people team, right? See, these things are actually the major concept. See, immutability is one thing that can eradicate a lot of issues, right? That can eradicate a lot of bugs that can occur in your code, right? See, purity versus side effect separation is one thing that can give you a clear understanding where to look at when there is a bug, right? Okay, let's go ahead.
So your slide, like only the PPT is being shared, not the slideshow.
Oh, okay. Um, so shall I continue? Mention that I'm moving ahead on the PPT.
No, like only the first screen of the PPT is visible, not the entire thing. Like it's not moving.
Okay,
Okay.
not sure why. Just a moment. Can you see now?
No, sir.
Let me represent them. Sorry guys. Let me share. Let me say entire screen then. Can you? Okay, let me present it. Can you see again? Can you see now?
Can,
Can you see why Haskell rather than only the first screen?
yes, I can see why Haskell.
Yeah. Sorry guys, like I didn't notice that the PPT was not being updated, but if someone was following, see, this is what I was previously talking. I'll just give a 1 minute summary. I said that it's based on lambda calculus, and these are the main reasons why functional programming language is something we all can look at to solve bigger and complex problems, right? And also, see, these things were one of the main reason that Juspay has been taken functional programming language, and we are doing well in finance, right? Okay, I'll just move ahead. I'll see. My plan is to show you some basic code, or base, like how do we write a code, right? Like basis of syntax, right? So how do you write a function? It's a simple. So let's say you wanted to write a function called add, right? You would take two integers and return back a third integer. See, that's what you see on the very first line. So add, see, the colon is again a syntax. You say int, arrow int. See, till the last arrow, everything is input. So in this case, it's like two ints were inputs, and the last int is your output, right? So add takes two variables, a and b, and all we did was a plus b. So it returns back the computed value of a plus b, right? So see, there is this one more interesting concept in functional programming is like by default you would think in your own data structures. It's not like you follow through the existing data structures. It's mostly because Haskell is too free for you to create your own types, right? So you can create random types to solve your problem rather than following what's existing, right? So let's say I want to talk about students who are interested in this session. So I just create this type. I just said data student. See, this is more syntax. So if something was not clear also, it's fine. You can ask a question, why is it written in that way? But it's purely syntax, right? So data student equal to student. And there are three fields in it: role, name, and interested in session. And as we know, role is an integer and name is a text and interested in session is a Boolean, right? So let's see, how do you define a variable which will be of this type, right? See, this is how you define a variable which will be of this type. And if you actually if you actually trace back to what is functional programming, you would understand why I called it a variable and it does look like a function, right? See, because in functional programming, it's all about functions, right? Functions are the first class citizens, and even if you say variable, it's more like a function call. It's giving a name to a computation, right? See, what is a variable? I say x equal to a plus b. That means I'm giving a name to a computation of plus between a and b, right? So that's the intuition that you get when you are working with functional programming language. So yeah, so initializing data is gonna more look like this. So it's again the same. If you remember the syntax from previous slide, it says Aravind : student. So that's the function signature of your function, and Aravind equal to student, and you have three fields, right? Role, name, and interested in session. And first one is an int, second one is a text, and third one is a boolean, right? Cool. Okay, see, there is this concept called sum type. So the one that you have seen previously, it's also a data type, right? But what is the type? It's actually a product type. So what do you mean by product type? You can see product type as an AND, right? A and D AND, or maybe conjunction or disjunction. I don't remember. Sorry. So it's actually an AND, right? So when I say product type, I mean all the fields in this type should be there, right? I can't say this or this or this. Like I want in the previous slide, if you remember, when we declared the type, see, I'm saying the student should have roll number, name, and interested in session or not, right? It's not like you can have one of the field and build a student in this data structure, right? You should have all the three. But there is this another concept, right, which is sum type declaration. So you want to talk about different kinds of students. So let's say Arvind or Paul or Vimal or in your terms. So let's say you want to talk about what are all hackathons you have attended till now. So data, your hackathon equal to DEVSOC or something else or something else or something else. See, you're attending any of these sessions, right? So it's more like it's a general, or if you can interpret in your general terms also, it's going to make sense, right? So, but see, the interesting point over here is I don't want to brag much about the syntax or these concepts, but the interesting thing is when you think, right, when I say what kind of data structures are possible, you might think like, see, I can write any kind of data structure. There is no generalization over there. But if you observe from here, there are only two types of data declaration. One is either a sum type or a product type. See, these kind of generalizations are possible when you're coming from mathematics. See, this is one of the main reason why I mentioned functional programming language is basically backed by mathematics, right? Because you get this generalization to not do the same thing repetitive, right? See, what is generalization? You kind of try to get it to a one more level on your abstraction thoughts, right? Like you kind of bring it up one more level than what we kind of think of. See, if I previous of these slides, if I ask you what kind of data structures are possible or what kind of data you can create, so you would have said like, see, it's, how can you say it's like million possibilities, right? But after this slide, you can say it can be either a product type or a sum type, right? See, data is different from data structure, right? See, the data you're going to put doesn't matter. I'm not going to care much about it because you are at the data type level. See, it can be either a n type or a sum type. Done. Now I'll go inside. That's another level layer of abstraction I'm opening up. But at least at this point, I have a little bit better abstraction than if I see it as a million possibilities of data structure. Why? Because you're merging data structure with data, right? Cool. See, I'm going to talk about one of the main thing that happened in computer industry. And if anyone follows, in 2009, the guy actually said it's his $1 billion mistake. Anyone can guess, but it's actually nothing but a null reference, right? See, there is this guy called Tony. He introduced null in 1965 because a customer asked him to do so, right? Because of some requirement of a customer, he has to create a null reference, and it is null as considered as a $1 billion mistakes in computer science is because it opened up a lot of doors for malwares. Even if you know the getS function from C is actually backed by null, and getS function is the first one who actually opened a way to write the first malware around 1980s, right? So null is considered as one of the biggest mistake, and he even called it as a $1 billion mistake because it actually costed a lot of dollars of time and $1 billion of money for a lot of developers across in this last 40 or 50 years, right? Okay, why do I talk about null reference? Cool. See, the very first, okay, before even going to the next slide, right? So the very first mistake of null reference is they said that null is a value that belongs to every type. So null belongs to integer, and null belongs to string, and null belongs to text, and null belongs to a list. Null belongs to any data type that you talk about, right? So they say null is a by default value for anyone, right? But you might have guessed, see, basically functional programming language is backed by mathematics, and you won't see these kind of I don't want to call it a hack or something, but it's more of a computer scientist hack, right? So where he involved that one variable. Okay, why did he involve? Because he can create variables without even assigning values at that point. He gonna assign the value later, right? So when there is this assignment concept later, like when there is a difference between, when there is a distinction between initialization and assignment, right? That's where you actually need the null concept, and those are the one of the main roots why null has been introduced. But if you remember, Haskell is functional programming is immutable, so you can't have this concept in by default. But anyway, see, mathematics doesn't support these kind of hacks in the first place. So hence, let's see what happens, right? So see, I wanted to write a head function which would return very first element of a array or list. To be honest, many people would think that, okay, what's great in it? All I'm going to do is say head, and I'll pass. See, that's just a data structure. Sorry, that's just a syntax of a list, right? Open bracket and close bracket, and it says it's of type integer, right? So many people would think I'm going to take that int and a list of int and return back an int, right? So that's what you would have thought, and this is how a function would be written, like head x colon xs is nothing but x is my first element, xs is rest of my list, right? So that's again a syntax. So you return the very first element. So many, like, usually if you're writing it in C or any other programming language, to be honest, you would have written it in the same way, right? You would have said, I'm going to give you an array of list and give me the first element of a list, right? Cool, makes sense. There is nothing wrong in it. But what would happen if the list is empty, right? I don't know what to return actually. So I just said that I'm going to return null, right? When the array is actually, list is actually null. Sorry, list is actually empty. I'm going to return a value called null. But is null is of type int? No, right? Because when you define the int, we said it's going to be from the range, right? Like if you consider it as a 4 byte, it's going to be minus 2 power 32 power 32 minus 1, right? So if you consider those terms, there is no value called null, right? So to be honest, you can't write a function like this in Haskell, right? Okay, even if you write, it won't compile. So the compiler itself is restrictive because it knows what is int, right? It tries to prove your program. So as I mentioned before, the compiler actually tries to prove your program. So it tries to prove your program for all possible values, and it will say, hey man, when I pass an empty list, you are returning back null, but null is not a type of int, so it won't even compile in the first place, right? So usually, how do you solve it? You create a new type. If someone remembers, this is mostly the sum type that we talked about before, right? So nullable int is either a just int or null, right? So the head function is going to be look like this, rather than how you have it on the left side. It's just a syntax, right? I can't write a function of head without using this, to be honest, right? Why? Because when it's an empty list, I don't know what to return, and I can't return 0, or I can't return -1, or I can't return null, because 0 and -1, logically wrong. But if I'm trying to return something called null, it says, hey man, I'm expecting an integer and you're passing a null, and I don't know how to append these two, right? I just want to give you a very small example of how bugs has been eradicated by the functional programming languages. So as you grow more, right, as you work on functional programming more, you would find these kind of patterns more. And we do consider at Juspay that functional programming language is one language, or you can consider it as a tool, which can give you actually a flowing, a running mat or something. All you need to do is just stand on it, so you will go ahead, right? So you can consider functional programming is something like that. It's a going mad, right? All you need to do is just stand on it. You will also go ahead at a faster pace than other people. Not a comparison, but just wanted to say that it really have that in its roots actually. So because it's coming from mathematics, and these all are just possible out of the box, right? Uh, See, you would notice this. I just really want to say one thing. See, I might talk more about functional programming. I would have said, okay, see, this will remove all the bugs, and it does this, it does that. But to be honest, see, it's just a tool, right? See, functional programming is just a tool that would help you to solve problems at a better scale, right? If you don't have a tool, right, you don't have a knowledge. Okay, let's not talk about it. If you have a tool and you don't have a knowledge, let's not even talk about it, because there won't be any outcome. You can't build anything, right? Let's say you have a very good knowledge, right, but you're not using a right tool, right? So again the same concept. Let's not talk about it, because you can't build an outcome. You won't get anything, right? See, let's say you wanted to swim, but you wore a spacesuit or something. So that doesn't make sense, right? Because your tools are not right. Even though you're knowledgeable, you don't know, everything about how to swim. You can swim for hours and all, but it doesn't work out, right? When in reality it just turns out to be a blunder, right? So we always see it in that way. So we should be knowledgeable, and at the same time we should choose the right tool, so that the outcomes will be more way ahead than what we usually expect for, right? So see, Haskell is one of these kind of tools where by just having it, it's just a tick mark. By just knowing Haskell programming language, it's just a tick mark. And I already explained various places why it is a tick mark in toolbox, why it can eradicate bugs and whatnot, right? So at the same time, you being knowledgeable is also one of the main thing that you should align with the tool, so that you can get a greater outcome, right? Um, okay, cool. See, I spoke. I thought I gave you a very good basic syntax, or an intro to functional programming. Even though, to be honest, it's mostly less than 0.5%, or even lesser than that, because we didn't actually cover main concepts of functional programming, which actually it is built on. I would leave that for your curiosity, or you can actually ask us back at Juspay. You can write to us. But yeah, let me talk about this PureScript-Presto. See, PureScript-Presto is a open source library that we have open sourced it in GitHub. You would find the repo, but it's about writing applications as mathematical equations, or writing app as how you see it, right? So let's say you're doing a bill payment. What would you do? There will be a splash screen before showing some operators. So once after that, you fetch all the operators, and you will show me the operators. You'll ask me for the mobile number. Then you'll ask me for how much amount to enter. Then you'll ask me for whether I should pay the bill or not. I'll just click a pay bill, and once the bill is paid, you will just show me the bill pay status, right? See, that is how the code looks like. The whatever the flow I have explained, right? That's how the code looks like in when you use PureScript and Presto, right? It just makes sense, or it just directly fits with your mental model of how an app should look like, right? See, these kind of frameworks are possible. At the same time, I'm not giving complete credit to functional programming language, but to be honest, functional programming is one of the main reason why something like this is possible with very easy. It's not even very complex stuff that Juspay has ever built. There are more complex stuff that Juspay has built, but this is one of the basic thing that we have built, and it just works like a charm, and it actually given a very diverse thoughts for us, and we have implemented a lot of things, and our goal is to write an app in one day, or a week, or try to see does that fit with the PureScript Presto framework that we have built. And it indeed seems like fitting, and we are on the direction towards making apps look more simpler than how they look in Android. Because if you're writing an Android app, you might be building a lot of UIs. It's just a complex code. You can't even understand where it starts and where it ends. You have to go through the code each line by line, and you have to remember what is the previous view. Did you put linear layout? All this stuff you have to be a little bit confused, and those all just goes away with the framework like this. And it is indeed possible because of functional programming languages and the concepts that were behind functional programming languages, right? Um, cool, guys. This is completely from my side. Anyone have any questions before? I can take few questions. Cool then. I guess that's mostly from my side. I hope I gave you a basic introduction about functional programming, and I have covered. At least I gave you a spark that you can look into functional programming, and you can actually indeed try out functional programming in different online platforms also, and you can actually check PureScript, Presto, and couple of other libraries that we have open sourced in GitHub of Juspay. Um, Thank you, guys. I guess now Paul will join and he's going to talk about property testing.
Hey, is everything fine? All right. Hey guys. Okay, I think it's time to start then. Hi. Okay. So, hi, I'm Paul. I am an architect at Juspay, and we all know what we do at Juspay. We do payments. That's our core business. So here I'm about to talk about property tests. Uh, so this has nothing to do specifically with any functional programming language or any specific language as such. It's more like a way of testing, and uh, it's not just about testing, but a way in which tests can be written. So yeah, let's get started. So okay, so what are tests? Tests are uh, uh, yeah, tests are uh, when you write a piece of software, you also write a piece of test to make sure that it behaves exactly how you wanted it to behave. So there are different kinds of tests. The most common are unit tests, which the developer writes. There are integration tests and regression tests. Integration tests are made written to make sure that uh, uh, if there are two modules which are individually tested, how do they behave with each other? So that's integration tests and regression tests. I mean, there's no clear separation between, like, this falls under the purview of unit integration or regression tests. I mean, tests can anyway kind of overlap, but the concept is that the general concept is that, I mean, unit tests are written by developers, integration is written by developers integrate stuff, and regression is generally written by everyone just to make sure that uh, things don't break across code changes and things like that. Yeah, so in this I'm going to like concentrate more about unit tests. So yeah, okay. So what is the purpose of test? It's to make software reliable and robust, but also it is a way to express the domain, right? How the domain is modeled. So say I, as a software architect, I want to like tell or a lead, I want to tell my team that, okay, like, what, this is how it has to be developed, rather than me telling in words. The software specification is more like a document which kind of like says more in English. More than that, a test kind of says that, okay, if your test passes these set of test cases, your uh, your code is behaving exactly what I need, right? And it also serves as a codified form of software specification. That's what it means, right? But let's take a simple example, right? Say this is in a language called Haskell, which Aravind explained some time back. This is basic form of sort function. I'm not really like proud of this sort function. So let's say sort takes a list of integers to a list of integers. So this is how you write a list in Haskell. So and this arrow says that it takes a list of integers and returns a list of integers, and sort. I mean, this is how you generally write code in Haskell. You say sort on an empty list returns an empty list. Sort on a list of on a single element. This means it's already sorted, so there's nothing to do there. And whatever this says that if there is a list constructed by head and this is the tail, so this typically means that your pattern match on the list and says that okay, like this is the head of the list, the head X is the first element of the list, X is the rest of the list, and you say that you filter all the elements which are less than X in excess, append it with a single element list which is X itself, and followed by the elements in excess which are greater than X. I mean, we're not really going to talk about the time complexity here, stuff like that, but let's assume that this sorts. I mean, this doesn't do a lot of other things. I mean, for example, this doesn't sort if there are sort properly if there are duplicates in the list, but it serves these purposes. I mean, like for the purpose of this talk, let's say. I mean, and let's say you as a software developer, you want to write some tests, you go ahead and write these 5 different tests, right? Say given a sorted list, you already give a sorted list, and the unsorted list you still sorted, and probably a 2-element list and a single element list and an empty list, right? So, but as a software developer, are you sure that you've covered all cases? I'm not sure. I mean, I do not know how many cases I've missed, right? So because I mean, when I say that I've tested for these, it exactly means I have tested exactly for these inputs. I do not have proof that I have tried more inputs, or if it will, even if the sort function works for more inputs, right? So this is what are the drawbacks of a traditional unit test. Say they're not expressive enough, they do not cover all cases, they're hard to mention. You have to go through and say, okay, this is my corner case, have I identified this corner case, okay, this corner case, and all these things, and then you have to like mention each of them. Also, they get unreliable over time. New developers add, remove, modify tests, so it's difficult to understand what the previous developer who wrote the test actually was trying to mean when he wrote a specific test case, right? So all these are drawbacks of traditional unit tests. All right. So, but back to our sort example. So let's give a mathematical intuition behind what is sort. So let's say, okay, so what are some properties which sort has to sort? So before that, let me like go back to this thing. So Dijkstra, the guy behind the Dijkstra's algorithm and great computer sciences, has told program testing can be used to show the presence of bugs, but never to show their absence. What this means is exactly what we have tried to. I've been telling you. So, like, say that. When you write a piece of software and write a piece of test, you have shown that for these test cases there are no bugs, but it doesn't mean that this piece of software doesn't have bugs, which is exactly what we need to tell anyway, right? Because that's what software testing is all about, or software development is all about, right? So what are some alternatives to unit tests? So there are, I mean, these are some things I just thought about. So one is you can write proofs. When I say proof, say something like let's say multiplying a number by -1 2 times gives you back the same number is a proof that I mean, let's say you want to write a piece of code which says that -1 is the, I mean, the negative of a number is the additive inverse of itself, right? So or the multiplicative inverse of itself, sorry. So then you can write a proof for that, but the language in traditional programming languages do not have this concept. The next thing you have is equational reasoning. I'm just going to skip this for now. So it's a paradigm which is available in pure functional languages like Haskell, where you can kind of like substitute and prove a program. The third one, which we are going to talk about, is property tests. So where you specify properties of a function or how the function should actually behave, and expect the system to generate enough test cases to figure out whether all tests have been covered, right? So these are the 3 variants. Okay. So now, so in case of sort, what is our properties? So this is a bit of mathematical notation, but I think it's I think people can easily follow. So so the first property says that if X is a list of integers and I and J are 2 numbers, and I and J are between 0 and the length of n, if I sort X, the ith index, the value at the ith index is strictly less than or equal to the value at the jth index. So this we know, I mean, like this is true for any sorted list, right? But this alone is not enough to say that it is sorted, because like, let's say I give me a list of numbers and I return an empty list, it's still true, because it's, but still the list is not sorted, right? So then you come back and write more properties. Let's say this property kind of says that every element in the input list has an index in the output list. This says that every element output list has element in the input list. That is to say that you've not introduced new elements while sorting, which is fairly okay to expect when you sort. So then you finally say that sort, when you sort, the lengths comes out to be the same, right? So these are properties, but how do you express these as code is a bigger question. Let's say what I've done is like, I've given you a bit of mathematical equations and asked you to do it. So how do we go about writing test cases for this? So let's see some property tests in action. So all right, so here I have a Haskell program, so don't worry about all the header and the prelude and stuff like that. Okay, so let's concentrate on this property. So this property says that for all lists which are in the range of 0 to 100, and the list consists of integers, reverse of the list is the same as the list. So here I'm not writing a specific test case to say that, okay, like say I have a list consisting of the numbers 1 to 100 in the exact order, and now reverse of the reverse of this list is going to give me back the same list. So here, I mean, we don't have the reverse function here, but it's pretty easy to write. But I'm just like saying, I mean, like I'm just going to hand wave and say that reverse is something we know. So then how do we test this function? So this is something, this is how I specify a property in this framework called Hedgehog, which is a property testing framework. So Hedgehog is able to specify these things like properties and for all. And here you say you can generate a list of arbitrary size. The size could be between 0 and 100, and the list could actually have numbers in itself. I mean, I don't know. I mean, this is just saying that the list is made up of only numbers. All right, so let's test this thing. Let's say, let's run this thing. I'm just gonna like say clean this out and enable this and just say, oops. Right, so what kind of happened is like, okay, it says that the test passed in 100. I mean, the test passed 100 different test cases. So that's what is the output. I mean, it's kind of pretty fast. So I mean, to quick check, you can kind of like, so not, this is not quick check. Sorry, this is Hedgehog. So Hedgehog, you can give the limit on the number of test cases you need, the kind of test cases you need, the you can also say, I mean, instead of having the elements of the list generated uniformly, you can also say that, I want more elements from the end and from the beginning. But this is a simple example that I've said, like, hey, okay, this is just trivial. So this passes. So let's go back to the next example. Let's say all right, so now let's say I have a pretty bad property. Let's say here is a property which says that I generate numbers. I generate two numbers, x and y, and I assert that x plus y will always be greater than or equal to x, right? So is this property true? Well, if you think about it, this property is not really true, because like I'm not told that you want only positive integers to be generated. Let's see how this gets tested out. Say, right. So I'm going to run this. All right. So okay, so now QuickCheck has told me that, exactly the code where I was. It told me that, hey, I tried with this input, which is some random negative number, and this is another random negative number, and here it said that x plus y is definitely not equal to greater than or equal to x. And this number is a huge negative number. It doesn't matter what this number is, but this number being negative is a problem because like anything added to the negative number kind of decreases. Right. So let's okay. So then let's figure out that, okay, fine. You know what? Uh, uh, let's go ahead and change our domain. Let's say I don't want negative numbers. So word 32 is the Haskell equivalent of saying unsigned integers, 32-bit integers. So the reason is 32 is it's a small implementation detail. Let's run main again, and it said that, okay, for this and this, x plus y greater than or equal to x fades. Right? So now, I mean, this is surprising. Let's say this is surprising. So like, why this should fail? Let's say so now let's add these two numbers and see actually what is coming through. So let's say, okay, it gave me this number. Okay, it looks like it's fine. So why should check or Hedgehog tell me that this is wrong? So let's run it one more time. It's going to run again, and it's going to give you a different set of numbers. This is my sorry, oops. I have these two numbers. Oops. Alright. So if you notice, this number is the same, which is as the sum from the previous time. So I mean, for people who were able to catch, this is exactly 2 power 32. And 2 power 32 is not representable in a 32-bit word. It's like the range of 32-bit unsigned numbers is 0 to 1 minus this. So yeah. So there. So I mean, so QuickCheck is able to find these cases for you. The other important thing to notice is that why is it that QuickCheck kind of didn't tell me that, you know what, I mean, it could have generated numbers which are like totally different. And this is not just a coincidence. It's not just a coincidence that these two came together. I did nothing special to say that, you know, give me exactly this number or something. That every time you generate the two numbers that are going to get generated are going to add up to this. This is by a property called shrinking. So anytime Hedgehog is going to find that there is a counter example, what Hedgehog will try to do is it will try to reduce the test cases to see exactly which of the test cases is going to which is the smallest test case which can fail. Yeah. So okay, let's see that in action. So let's say I'm just going to like put a trace show here. So just say okay, I'm just like say show ID of x and y. So this I'm just so this is syntax for printing the number x plus y. So since Haskell is a pure language, we really can't put prints anywhere because print is actually a side effect. So we have to go around these things. And trace show is one of these functions which kind of prints, but prints on very specific circumstances. But I think here it might just print what we need. So let's say how it works. So right. So again it failed. But actually, if you look at it, okay. So yeah. So it started off with this this number, and this. So this kind of like would have been fine. It would have been fine. At some point, it would have found that, okay, I think like this is 4256. Fine. So somewhere it finds that, you know, okay, this test is, I think that should be more evident towards the end. Let's see. Right, so these are all the things. Okay, I think like. 29, 39, 45, 47, 48, 49. Okay, so it did 49, and then it went to a little bit above, and then it went a little bit above, and then it figured out that, you know, where is it stopping? So somewhere it figured out that this number is going above the limit, and then it's going to like figure out, okay, that this number is going above the limit, and so it does something called shrinking. So what shrinking does is it kind of reduces the test case's size. In the interest of time, I'm going to cut this short and move on to the next one. I'm just going to comment this out because it's a failing test case. It passes. All right. So this is another test. So this is another merge sort function. So this does merge sort, but the time complexity is different. So I do not know. I mean, so in the interest of time, I'm just going to say that there is a small bug here. The bug being that if I find two lists and I find that x is lesser than the merge function has a list has a bug where I say that, okay, if x is less than y, I actually managed to write this bug. So long time since I kind of like wrote any sort function. So when x is less than y, I just did x cons y cons merge x's and y's. Otherwise, you just do y cons x cons merge y's and x's. And so here we have this property which we described in the slides, right? So whatever we described here is oops. Is expressed here. So what this says is that this thing says that, okay, merge sort actually sorts. This is the assertion of the function. This says that, okay, you fold over the list and you check for every element if this is lesser than the previous element. Start with true and the lowest element and check if it is if it always returns true. So, and this is going to run over all lists of the range 0 to 1000 with numbers in the range 0 to 1000. You can like can increase the range, but it's of no use. So okay, let's say, so let's run this and check what happens. Let's see. So oops, sorry. Let's run this. So it says that this fails on this test case if I have 1 0 0. So if I kind of like say, if I say merge sort 1 0 0, this is from my implementation. So it's not working. It definitely doesn't sort. So it's clear it's not sorted. So let's go fix the bug. So the bug here is that sort of if you figure out that x is smaller than y, you don't take the element, the y element itself, but rather so this now. So you do a couple of unit tests this way, then you go ahead and say, okay, fine. Okay, so here it kind of like has to. Okay, so this is because we had a trace somewhere. Phrased. So pass. So it's not really a big thing, but yeah. All right. So now if you actually go and reload, it sorts after the bug is fixed. Right. So any questions in the meantime? Check. Right. We can proceed. Okay. So okay. So also similarly, I have these things which say that merge sort does not remove elements. Merge sort doesn't add elements. Is another property. Similarly, so you can go ahead and so these are our comments done. Right. Oops. Make sure that all our tests pass. Oops. And it ran 100 tests for each of them and make sure that it's really doing as it is expected. By the way, if you notice in all these three cases, I have not written a single test case explicitly. I have always specified properties and asked the system to generate test cases and check. So this is how quick check is beneficial. So you don't have to like actually write test cases for this. So rather you can kind of like say that you can specify properties of programs and ask them to be verified. So let's take this a little bit more away from sort and stuff like that. Let's say we are modeling a bank, right? So here we are having customer ID to be an integer, money is a word. The reason it's a word is because it cannot be negative. We'll say our bank doesn't take negative numbers for money, and bank is a map from customer ID to money. It's a very simple concept of a map of a bank, but let's stick to this. We're going to use some helper functions. So the total balance is going to be like you get all the elements of the bank, which is going to be all the money, and you then sum them up. The customers are going to be the keys of the map, which is the customer IDs. So this is how you specifically write it in Haskell. So customers is a function from a bank to a list of customer IDs, and you just give the list of keys. So these are all helper functions which I'll be using later. So just and let's say we are going to define something like a bank operation, which can be a operation which could be either you withdraw, a customer comes and withdraws some money or deposits some money or transfers money from one customer ID to another customer. You add a customer with an initial balance, or you remove a customer. So you can think of them as Java interfaces to operations, and you specify each of them as classes. But this is, you can write so concisely with Haskell. The reason I'm choosing Haskell is that it's easier to write these and show these rather than show a lot of code. So yeah, and let's say there is a bank operation. Okay, let's define this function called operate, which takes a bank operation, which is one of these operations, and which transforms a bank to a bank. So in the real world, you don't really have an input bank and an output bank, but for the sake of simplicity, because Haskell doesn't have these immutable variables, you're going to like take a bank and return back a bank. So this is like your things in if you've seen Elm and time travel, something like that. So you can kind of like go back in time to the bank which was operated on, and also on the bank which is coming back in the future and things like that. So right. So this is not going to do anything fancy. So when someone tries to withdraw, you just check if the balance is greater than an amount. You then you change it. Otherwise you don't change it. Deposit doesn't do the check. You just deposit. Transfer checks if the amount is greater than the amount he has to transfer. And so if so, it allows the transfer. Otherwise it doesn't allow it. So we're not like raising any exceptions or anything like that. We're just going to like say that okay, people are going to be good. They're going to like they're just going to come and say okay, fine, if this bank doesn't allow me to transfer, I'm just going to like come back later or something like that. So add customer, the customer comes and you want to add him, he has a new money. What you do is you need to generate an ID for him. The simplest thing you can do is like look at the size of the bank. This is the size mapped out size of the bank, and then you insert you increment the ID, and then you generate and then you insert him into the bank, into the record of banks to customer to money. Just removes it. So okay, fine. So let's say, and these are some helper functions. Random money generates numbers in the range of 1 to 100,000. Non-empty bank. So these are helper functions. So this is how you generate a non-empty bank. So you just generate a random size. So the way Hedgehog works is that it works on the size parameter. You can kind of like tune the size parameter, but for now we are just going to like take a random size of the bank, and we're going to like generate as many customers, and we're going to add them to the bank. So this is just a recursive function which does that. Whatever it is. But this trust me when I say that this works exactly it has to. So yeah. So by the way, the code for this is available on GitHub. You can go and check it out. I think it will be there in the comment section later. So this is a non-empty bank, which could be a bank with just one customer. We also have another customer function which has more than one customer. Okay, so now we want to randomly generate these operations as well. These operations of withdraw, deposit, transfer, add customer, remove customers also is something we might want to randomly generate. So this is how you generate them. So this is a specification of how you generate them. You're not till now we have not actually generated things. So we are just saying that okay, like so gen.choice is a function which looks at any of these things and generates one at random. So it will either give you a withdrawal or a deposit or a transfer, or create a customer or remove customer with equal probability. And right, so okay, so now let's so these are still some helper functions. Okay, so now let's look at some properties which we think the bank should. I mean, if we write some code, let's say the bank should. I mean, let's now test out our operate function. Operate function is the crux of our code. So I think we are short of time. So let's say quickly. Let's say so that's one of the things we want to like say is that deposit increases the bank balance. This is not always true because deposit because let's see how this is not really true. So I'm going to like comment it, these and then say check this, run this. Went through fine. The reason is okay, so the reason that this thing is like I've said that okay fine, you know what, my money can be in the range of 1 to 100,000. So in this case, like I'm always going to, my balance is going to increase. So but if let's say my money is in the range of 0 to 100,000, this property might not hold anyway, because like okay, so here is a counter example that the system was able to tell me. So if I have a bank which had one customer with a 0 balance, and so I generated again money 0 and the customer 1, and I deposited that money. My balance is not going to change. It still says that my balance is going. The first customer is still going to have money 0. So QuickCheck has already given me a counter example. Sorry, Hedgehog has already given me a counter example to say that this is a invalid test case, right? So let's go back and change that. Oops. Right, so swing back many to 1. Okay, and right. So another property is we can check is when I transfer money between two people, the total transfer of the total amount in the bank is not going to change, which is also trivially true. You can test it out. So that is going to pass as well. So no problems there. So transfer reduces the balance is something I'm going to skip for now. Okay, let's look at a very interesting property. We'll just be done in a couple of minutes. Let's say I generate operations for a customer, and let's say I have a bank and I want to generate operations which are not involving a specific customer. I would expect his balance to remain the same. While this looks like a very trivial property to be held, there is I mean, everyone can expect that, right? I mean, let's say you have a bank and one customer does not come and transact, or no one actually puts money into him. So I mean that also. So you would expect his balance to be the same. So right. So that is something you would expect in a bank. So let's try out that. All right. So here is a counter example. So what this says is that let's say I have two customers. The first customer has balance 1. The second customer has balance 2, and I'm going to remove customer 1. Right. Remove customer 1, and the randomly generated customer for me is 2. Right. So I'm just going to make sure that I generate operations which do not involve the customer 2. I remove customer 1, and then I add a new customer with money as 2. This is not his ID itself. So I add a new customer with ID with money 2. This fails. So it's saying that, I mean, and it also tells me what is the failure in the test case. It says that, okay, it is supposed to be, so LHS is like the pre-operations. It says that, I mean, before the before the operations it was 1, but after the operations it became 2. So so is anyone able to figure out why it happened this way? By the way, we've not done anything to customer 2, right? So so would anyone be able to guess? All right. Okay. So the reason I think is okay. So the reason we have this bug can come in is because when we remove a customer and we add a customer, what happens is that we generate a ID which is one more than the one more than the size of the map. So when we removed the customer 1, what happened was that the size of the map was 1, and when we added the customer, the size of the map was the new ID which got generated for him was 2, and we added a new customer with ID 2 and money 2. So when we looked up, it was different for him. So that was the bug. So yeah, so this brings me to an end to this presentation. So any questions I would like to take now? All right. Okay. Thanks, everyone. Okay. Over to you guys.